Okay, well, we left off on our introduction to C at pointers and arrays, and so I'll briefly run down what we had talked about. We had an array Z of 10. We can use two different ways of accessing this. One is via the square bracket notation, so Z of I returns the ith element of the array Z, and the address, the AND of Z of I, gets the address of the memory address of Z. If you use Z by itself, this actually returns the address of the start of the array, so the 0th element. So if you see Z in a program, this is equivalent to the address of the Z of 0 element. So here's an example. You can have an integer pointer IP. You can declare an array Z of 10, and then one of the things you can do in an assignment statement is set the integer pointer IP to equal Z, and this is equivalent to setting IP to the address of Z of 0. Okay, so there are, again, multiple ways of accessing arrays, and one way you can do this is via pointers rather than the square brackets. And so sequencing through a character array or integer array, one of the ways you can do it is to declare a character pointer, CP1, or an integer pointer 1. And if they're pointing to the different either character array or integer array, you can get successive elements of that array by simply incrementing the pointer by 1. Now, because of the data type associated with this pointer, the increment is going to either is going to increment by the size of that data type. So, for example, CP1++ increments the address stored at CP1 by 1 because the character is size 1, and IP1++ increments that address by 4 because the integer is a 4-byte quantity, and so every successive element of that integer array has the addresses differ by 4. And so here is some C code that sequences an array using pointer arithmetic rather than the square bracket notation. Set an integer pointer to declare an integer pointer IP, have an array Z of 10, set IP to Z as we had before in the previous slide. And then if you do IP plus equals to 3 and star IP equals 100, well, what is this going to be? So first of all, we'll ask these two questions. How much larger is IP than Z? So pause the video and come up with your answer. And this is going to be 12 because you're going to increment the integer pointer by 3 integers. So you're going to move 3 integers over, which is for an integer is 4 bytes, so 4 times 3 is 12. And this is in decimal. And then, so which element of Z is set to 100? Well, this is equivalent to going to Z of 3 and then setting what is at Z of 3 to IP. So this is IP plus equal to 3, star IP is equal to 100. Well, these 3 instructions, setting the integer pointer to the beginning of the array, incrementing that pointer by 3, and then setting what points to what IP is pointing to 100 is equivalent to Z of 3 equal 100. Okay. So the next quirk of C is, well, I shouldn't say a quirk, but something that you should know about with C are a function called parameters. And so in C, all function arguments are passed by value. So what does this mean? This means that the called function, or the callee in this case, is given a copy of the arguments. So when the caller wants to call a function, he copies the arguments that he wants to pass to that function to the callee. And so what does this imply? This implies that the callee can't alter a variable in the caller function. And it can only alter its own private copy that's given through the arguments. So here's an example of a callee, a function called swap1 that takes 2 integer parameters, and it gets a local variable temp, sets temp to one of the parameters, sets that parameter to the other parameter b, and then sets b back to the initial parameter. So this appears to swap these 2 integers, and if the caller calls swap1, so in this case the caller has x is 3 and y is 4, after a call to swap1, what do you think the values of x and y are in the caller? Not within swap 1, but in the caller. Is it going to be x is equal to 4, y is equal to 3, or is it going to be unchanged? X is equal to 3 and y is equal to 4. So again, pause, come up with your answer, reason about it, and then I will explain it. So because it's call by value, you will see that for this particular call, the parameter 3, the x is 3 and y is 4, these two values are copied to swap 1. Swap 1 does the swap internally, but because you're swapping the copy of it inside swap 1, the values stay unchanged. So call by value is the default, but there is a way to do call by reference in C. So here's another implementation, swap 2, and the way you do call by reference is to pass pointers rather than the actual value. So swap 2 takes a integer pointer A and integer pointer B, and it sets this temporary variable to whatever A points to, and then it sets whatever A points to whatever B points to, and sets whatever B points to the original thing copied from whatever A pointed to. So if you think about this, you're going to pass two memory addresses to swap 2, and it's going to dereference those memory addresses and go to those memory locations and swap those values. So in this case, if the caller has two integers, x is 3 and y is 4, but instead of passing x and y directly, if it calls swap 2 with the address of x and the address of y, and then subsequently tries to print out for x and y again, then what is going to happen? So will it be A1 where x is still 3 and y is still 4, or is it A2, x is 4 and y is 3? So stop, pause the video, reason about it, come up with your answer, and then I will explain. So in this case, because you're passing pointers to x and y, and these things are dereferencing them on the inside, you're actually getting at the actual values for x and y. You're able to change them, and so after this swap call, you have swapped the two values of x and y. Okay, so this elucidates the difference between how call by value is done and call by reference is done in C. So call by reference is implemented via pointer passing. You pass pointers to the objects that you want to change, and then within that function you can change what those objects because you have a pointer to them. All right. Otherwise, the rest of your calls are call by value, in which case you copy. You have a copy of those two integers copied to the callee. And in this case, you're actually copying the two pointers to the callee when you pass pointers to swap, but we'll get to that later. Okay, another interesting thing with C is that assignments and expressions are related in that assignments actually return an expression. So in this case, when you set x is equal to 4, if you put that in parentheses, it will return 4 as the value of the expression in C. So if you have this statement, if x is double equal to 4, we talked about earlier, the double equal operator is an equality operator. It's a logical comparison. And so this will only set y to 3 if x is in fact 4. But when you have this statement, if x equals 4, set y equals to 3, because x equal 4 is always going to return 4, it turns out in C, any non-zero expression evaluates to true. So in this case, y is always going to be set to 3 because this this assignment is always going to evaluate to 4, or true. And so you might think that this is a useless statement here, but you'll actually see assignment within an evaluated expression in multiple places in C. One of the most common places that you'll see this is in a while loop where you're trying to get input from the standard in, and you're continuing to try and get a character, but when this character that you get is the end of file character, you want to terminate this loop. So while C, this expression is going to assign C to the very next character, and then we'll break out of this while loop whenever that character is the end of file. If it's not the end of file, then you can actually utilize this character C within the file loop in C. Okay. So this is interesting because the difference between equal and double equal was in fact tried, and a hacker tried to leverage this to insert a backdoor in Linux about a decade ago. And so this is the link down here if you're interested in reading about it. But in the Linux system, in the Linux kernel, there is a function, and this function was called wait2 or wait4, I think is the function name. Where is it on here? Yeah, wait4. And within this function, there is an if statement, and it checks for options that were given to this wait function, and then it checks to see if your UID was 0, and it did specific things if you were the administrator. So if you have a user ID of 0 on Linux and on Unix, this means that you are the root account or the administrator account, and you have special privileges. Well, if you look at this if statement, as soon as you evaluate this expression, within the kernel, this will set the process's user ID to 0. So this will instantly give you root privileges if this was slipped into the kernel. And fortunately, this was caught. But this is an example where when you're looking at source code and trying to audit it, this is one of the things that you have to watch out for is an improper use of the assignment operator rather than the equality operator. Okay, so we're going to wrap up your introduction to C with JPL's power of 10 rules. Now, a lot of the C programming, well, you see a lot, in this day and age, a lot of the C programming is done on Internet of Things devices, embedded systems, systems that don't necessarily have the resource capacity to run an interpreter, like a Python interpreter or a JavaScript interpreter. And so the power of 10 rules are sort of things to think about when you're programming C to keep your program as safe and secure as possible. So this is intended for mission-critical, safety-critical applications and they're used to improve the quality of your code. So rule number 1 is to restrict all code to very simple control flows constructs. And this is for readability. So what you want to do is avoid things like go-to statements or jump statements that don't allow someone to understand the flow of control in a single page, for example. So this makes your code easier to verify in terms of code clarity. Someone else can read your code and be able to understand it a little bit quicker. It's said in many software development environments, you spend 80 to 90, like for large software projects where you're working with a lot of other code. It is said that 80 to 90% of the time is spent reading code to figure out how it works. And if you are leaving code for someone else to modify, you want to make sure that it is as easy to read as possible, and that's what rule number 1 is getting at. Rule number 2, all loops should have a fixed upper bound that can be statically proven. And this is to prevent runaway loops, sort of infinite loops or loops that have sort of an unbounded runtime. Because again, predictability is something that you would like to have in your code. Rule number 3, do not use dynamic memory allocation after initialization. So the idea here is to allocate all of the memory that you need up front, because if you have a long-running process and you have dynamically allocated memory within it somewhere, and it's running in a loop, and you aren't disciplined enough you don't have the discipline enough to free all of the memory that you're no longer using, then you could have what's known as a memory leak, and then basically after a certain period of time, your device will run out of real memory and cause a hit on your performance. Other issues with dynamic memory allocation is really easy to inject memory corruption bugs using dynamically allocated memory. Web browsers have had a really difficult time getting this to work. And I referred to Rust earlier. One of the nice things about Rust is that it forces strict memory discipline on your program, which gets rid of a lot of bugs. Rule number 4, and this is similar to the previous rule number 1. What's it? The clarity one. No function should be longer than what can be printed on a single sheet of paper. And each function should be a logical unit that is understandable and verifiable as a unit. And so this is a pretty straightforward rule in terms of readability and understandability. Rule number 5, the code should average a minimum of 2 assertions per function to check for anomalous conditions. So you should sanity check. Asserts are little checks in your program to sanity check the state of your program. And typically you'll see in production code a lot of pre-condition verification and post-condition verification of functions and their parameters and their return values, just to make sure what is given to these functions is what you're expecting. And then anytime an assertion fails, it should return these error conditions to the caller, and it should be checked, and it should be made to fail safe, basically fail in a safe condition. Okay, and so the estimate is that as you're programming, a defect will occur in 1 line out of every 10 to 100 that you write, and so assertions help you catch them very quickly. Rule number 6, data objects should be declared at the smallest possible level of scope. And this allows you to hide data from other parts of your program to keep them from getting referenced or corrupted from outside of wherever they're being used. And so this confines your state to wherever it's actually needed, and allows you to diagnose errors because you sort of compartmentalize the state that you're storing and operating on. Rule number 7 is the return value of any functions should be checked by the calling function. So the validity of the parameters should be checked inside of each of these functions, and then the return values should be checked just because of error conditions need to be sort of identified quickly. It's often the case that when we program in C, we'll ignore the return values all the time because it's quite verbose to have to execute a check on every libc library call. So you'll see in many production C environments there are wrapper calls, and those wrapper calls within them will check the error code so that you can make your code more concise. Rule number 8, and this won't make much sense to you until we talk about what the preprocessor does, but there are ways of doing string substitutions using the C preprocessor via header files, for example, like standard io.h header files. The idea of rule number 8 is to limit the preprocessor use. So when I introduce preprocessor rules, you'll see that you'll want to limit how you use them. Okay. Rule number 9, restrict the use of pointers to no more than 1 level of dereferencing. And also, function pointers should be avoided. So in the first case, it's really difficult when you start to think about pointers to things. For example, argv is 2 levels of pointer dereferencing to get an argument. As soon as you get beyond that, it becomes hard to reason about your program. If you have a pointer to a pointer to a pointer, and you're trying to figure out in your code whether or not it's used properly, the fact that you have these multiple levels is extremely confusing. The other issue with function pointers is that it's hard to statically validate the program state and where you are along the path of your program, your control flow graph, if you're using a lot of function pointers in your code. And so for performance, you might want to use them, but unless there's a really good reason for using them, they should be avoided. Let's see. And then the final rule is that you want to compile all your code with all of the compiler warnings enabled. and you want to make sure your code passes with no warnings. And so a lot of things that become errors are initially warnings, and so you always want to make sure that your code clearly compiles. All right, so that's it for the introduction to C. See you next lecture.